We are going to start the lecture 11. As I mentioned in the very beginning of the course, the half of the lectures of this course will be on architecture, how nanostructure developed in different kinds of natural and man-made materials, followed by thermodynamics and surface energy. So, in the first case for the architecture, we have discussed many such examples of natural materials. We have not discussed much about the man-made materials, which we will discuss obviously. Then I started discussing about surface energy. The surface energy and thermodynamics, they are interrelated. So, I have to go back and forth, as you know. So, in the last lecture, we started learning a lot of things about thermodynamics, right? As you know, thermodynamics is a very basic subject of material science and engineering and metallurgy also. A lot of things can be explained using the thermodynamical principle. So, in the last lecture, I introduced several important aspects. I introduced what is the change of temperature, change of vapor pressure, change of melting temperature, in fact chemical potential also. Today we are going to continue some more discussions. In fact, we are going to go to basics even, because after analyzing the lecture, I understood we should do much basic things for you to understand the subject. Well, the most important aspect when you talk about nanomaterials and thermodynamics of nanomaterials is the effect of size. How the small size can affect the thermodynamics of material, so that we can understand various kind of properties later on much easily. Well, so as you know, thermodynamics mostly talk about solutions. Well, you know, pure metals are not solutions, although there may be dissolved oxygens, nitrogen, or maybe some moisture, but we never bother much about that, because they will be very small amount, like in fraction of a weight percentage, or maybe in ppm level many cases. But they are important for various applications in nanoscale, like gas sensors. Nonetheless, we will be dealing with various alloys, right? And alloys means solutions. What are solutions? Well, you know liquid solution. Okay, liquid solution is what? If I take glass of water, okay, if I take this water, okay, this is in a container, this is my water bottle, and I pour salt into it, maybe 1 teaspoon of salt into it, and then do such a kind of a vigorous stirring option. So, what will happen? It will form a very nice solution, right? Salt water solution, which is easily available in seawater. Okay, that's why we don't drink seawater, because it's salty and it's sour. It doesn't taste good. We always like to have a water which is sweet. Okay, so many cases people like to add sugar into it. You can add another teaspoon of sugar, shake it up, you form a solution of sugar and salt in water, which is good for many kinds of fatigue, or sometimes you may have stomach upset, you can use it, right? But that's the solution in liquid state. Same thing in solid state is also solid solution. There is nothing, no difference at all. So, you have to put one into other. Here you have A and B. A is bigger, B is smaller. You are adding B into A, so that B get dissolved into A, just like salt get dissolved into water. Water content was bigger, salt was very small, 1 teaspoonful, right? Same thing, you are putting small amount of B into large quantity of A, then there is a solution of B in A. It can be vice versa, like you have a large quantity of B, then you add small quantity of A. Let us give an example of very common steels actually. Steels have very low carbon, less than about 1 weight percentage. Like in 100 grams, you have less than about a gram of carbon. 100 gram of what? Iron. You have iron as the base material for steels, right? Correct? You know that. So, that means you are adding carbon into iron to make a silane solution? Well, steel has many phases like gamma, austenite, alpha, ferrite, delta, ferrite, many solution phases exist. So, silane solution is very important concept. Now, why do the solution get stabilized? That is why thermodynamics can be explained easily. Why do I add salt into water and shake it up and it forms liquid solution? That must be something happening in the material. Well, so that is the thing actually. So, by the way, to differentiate between a silane solution and a physical mixture, let us compare this situation. You have a suppose sand. Sand is easily obtainable to you, right? You can go to a beach and you can get sand. And you add a little bit of salt into it and mix them together. They will never mix each other. Pure sand, dry, with no water, salt dry, with no water, will never mix each other. They will remain as a physical mixture. So, that is, if I have to calculate the free energy of the physical mixture, this will follow the straight line. You can see that? That is the line. So, as you keep on adding the salt into the sand, linearly the free energy of the system will increase. Okay? Free energy is nothing but G equal to H minus Ts, right? This we have discussed many times. That is what is free energy is, okay? This is gives free energy. G equal to H minus Ts, right? That is equal to Gibbs free energy. It is given by Gibbs. That is why. So, it is the difference between enthalpy minus T into entropy. T is the temperature. So, that is how it will vary. Now, the moment I form an atomic scale solution, what is that atomic solution? That is what is written here, right? Intermixed. Like a salt, if you put in water, shake it up, it forms an intermixed liquid solution. Something is there in solid also. That means you can't separate the atoms from one from other. If you mix sand and salt, you can separate them out very easily. You know how to do experiment, right? I am not talking about it. It's 10th, maybe 7th or 8th standard experiments students do it in the schools. So, that is the thing actually. So, that if you do that, if you form atomic solution, free energy actually goes like this. Okay, that is a parabola. You can see that. So, free energy drops drastically if you form atomic solution. Why does it happen? That mostly happen because of Boltzmann. Okay, because of Boltzmann that we discussed in the last lecture. So, Boltzmann gave an entropy. When the moment you mix two atoms together, entropy increases. That is what it is, G minus H equal to minus Th. This term increases, and that gives you the basically delta Gm, and delta Gm is mixture actually M for mixture delta H M minus T delta Sm. So, now question is how do you calculate delta Hm and delta Sm, right? That is something which you need to know very well, correct. So, therefore, today we are going to see that. So, as you have seen, delta H mix or delta H M, M for mix I told is equal to delta H mixed states minus G unmixed states. When you mix them atomistically together, when you compare the unmixed, that is your delta H mix minus T delta S mix, correct. So, that means we need to have ways and means to calculate delta H mix and delta S mix. Delta S mix can be easily calculated using Boltzmann hypothesis, that is S equal to K, L and W can be used to that. But what about delta H mix? Well, let us do that. Okay. So, the most important thing about delta H mix is, let me do it here. Okay. Delta H mix is what? Correct. Is the model given by quasi-Mel theory. What is that model? Let us consider, okay, I'll talk from various sources, mostly from, let us consider 1 mole of a solution consisting of 2 components A and B, right? And there are any numbers of A, any moles of A and NB moles of B, correct. So, then we can calculate the mole fraction of A and B as what? If Na moles of A and Nb moles of B in a solution exist, the mole fraction of A is Na divided by Na plus Nb. Na moles divided by total number of moles. Similarly, Xb, Nb plus Na plus Nb, right? Okay. Now, so many cases, AB atoms are situated in a solution, there will be lattice, okay, is it not? This is solid, crystalline solid, there will be lattice. So therefore, some places A atoms will seat, some places B atoms will seat, okay. So that means some places AB will form bonds, some cases A will form bonds, some cases BB will form bonds, depending on how they are occupying the lattice, right. This all probability exists, you agree with it not? There is these three types of bonds can form. Let us suppose the bond energies of AA bond is bond energies EA, these are all bond energies, VB, EB and AB, EAB. So let us write that EA, EBB and EAB. Three different bonds and three different energies. Now, what else we need? We need to know also number of bonds AA type, BB type, AB type. Let us suppose number of bonds are AA type is PA, BB type is PBB and AB type PAB. Am I right? So therefore, in the when you mix them together, total bond energies, I write E mixed. When you mix them together atomistically, is number of bonds of AA multiplied by bond energy of AA, number of bonds of BB multiplied by bond energies of BB, number of bonds of AB multiplied by number of bond energy of AB. Right. Now, any crystalline lattice there will be specific coordination number, like an FCC coordination number is 12. That means one atom is surrounded by 12 atoms. HCP also. BCC, remember, you can go back to my lectures, it is 8. It is a center atom and surrounded by 8 atoms. So 8 is the coordination number. So nonetheless, if suppose Z is the coordination number. If Z is the coordination number, Z is the coordination number, then there will be how many A type atoms? A types atom, type of atom, obviously will be equal to Na, Na is the moles multiply Z, Z is the coordination number, correct. Now, this is talking about A types of atoms, okay. So, it will also have two types of bonds, A bonds and AB bonds, that is possible, right. Obviously, both cases A is common. So, A atom is present in both cases, whereas A or AB does not matter, A is common. So, now we have to calculate how many of these are A and how many of these are AB. So, I can write down easily NaZ, total number of A atoms in the 1 mole of that solution is equal to PAB, PAB is the number of AB bonds plus 2 into PAA. It should have been PAB plus PAA, but we are adding 2A PA. Why? Because factor 2 is basically because each AA bond has 2 atoms, but on the other hand each AB bond has 1 A atom. So, PA is number of A bonds, each bond has 2 atoms and we are calculating number of A atoms. So, therefore, this is must be used, correct. So, let us write down these as equation number 1. Similarly, I can write down NBZ, that is equal to PAB, NBZ is number of B atoms, to PBB. I hope this equation is clear to you, right. Why the factor 2 is coming? Factor 2 is coming because each A bond has 2 A atoms. So, you have to double the number of A atoms for one bond, that is why. So, easily you can solve these two equations, okay. A and B, 1 and 2 equations, that will give you PA is equal to NAZ minus PAB by 2 and PBB is equal to NBZ. You do yourself, right. I am not doing, but it is easy. Basically, you have to subtract, then only you will get very easily. So, now let us calculate E mixed. So, now we know how many A bonds, how many B bonds, one and this A, B, B, A, B, everything we know. So, what is E mixed? You remember, E mixed you have written like this: PA, EA plus PBB, EBB plus PAB into EAB. So, okay. So, now we are putting those things. So, PA is what? NAZ minus PAB by 2 into EAA. Similarly, NBZ minus PAB by 2 into EABB plus PAB EAB, right. So, we can always simplify it very easily. What? NAZ by 2 EAA plus NAZ by 2 EBB plus EAB minus EAA plus EBB by 2 into PAB. That is what you will get, correct. So, as usual, like last classes, we will erase the top part, keeping some important things on this. Okay, so that is the mixed. What about unmixed states? When if you do not mix them, like sand and salt. So, E unmixed, that is very simple. PAA, EAA, PBB, EBB. There is no bond between A and B, unmixed, right? They are getting separate. So, therefore, this can be written as NAZ by 2 into EA plus NAZ by 2 into EB, BB. So, delta G, delta E basically is the mixed, difference between mixed and unmixed, that is nothing but E mixed minus E unmixed. Okay, it is mixed, not mixed. That if you do the mathematics properly, what you will get? You will get simply this equation: EAB minus EAA plus EBB by 2 into what? Into PAB. That is what you will get. Correct. Now, in solution theories, such a kind of quasi-chemical theory what we are talking about it, This is what quasi-chemical theory. In quasi-chemical theory or like this, we assume that when you mix A and B together, there is no volume change. Mix them, that is very unlikely, but it can be considered. So, in that case, so therefore, delta H mix is what? Delta H, this is delta E, correct? Delta H mix is equal to delta E mix, internal energy change, P into delta PM. So, you have used delta PM as 0 volume change, we have already assumed. That is what is the assumption of delta of quasi-chemical theory. So, that means since delta PM 0, so therefore, delta HM is EAB minus EAA by BB by 2 into PAB. That is what it is. So, what does it tell? It depends on the bond energies differences of the dissimilar bonds minus average of the similar bonds. So, delta H mix sign will depend on difference of these terms from EAB and the half of EA and AB. Right. So, now basically the problem boils down to how to find out the PAB. Well, problem is now to basically find out PAB, right? Well, so okay, now we know that mole fraction of A, mole fraction of B, mole fraction of A, mole fraction of B very easily, right? We know very easily. So, mole fraction of A is XA, mole fraction of B is XB. So, we can always consider probability of any A atom situated next to A atom as XA multiplied by XA. Probability of A atom sitting in the lattice is XA. So, probability of finding another A atom close to that atom is XA into XA, XA square. It is very easy. If I have A atom here, so finding this A atom in the solution probability is XA, that is a mole fraction. Now, I want to find another A atom here, so that AA form bonds, probability of finding that is XA. So, this probability of forming this bond is XA into XA, that is XA square. Same thing is true for B. So, now probability of finding A atom here and then B atom there is what? XA and XB. But you can also have situation like this, probability of finding B atom here, then A atom here. The bond is same, like that is between A and B and A is the AB bonds. So, that is also XA, XB into XA. So, therefore, probability of finding AB bond is 2 into XA and XB. This is also true, this is also true. But probability of finding A bond is XA square, BB bond is XB square, correct. So, I can write down now, knowing these aspects, PAB, PAA is equal to half of Z if it is 1 mole, so contains Avogadro number of atoms into XA square, PBB is half of Z N0 into XB square, and PAB is half of Z N0 into 2XA XB. That is nothing but Z N0 XA into XB, right. This 2 and goes down. So, now let me erase some part to come to the conclusion of this quasi-chemical theory. The conclusion of this quasi-chemical theory is that delta H mixed is nothing but EAB minus EAA plus EBB by 2 multiplied by Zn0 XA XB. And you know EAB, EBB, EAA, Z N0 all are constant for a particular system. When you consider AB type system, between two elements, it is fixed. Bond energy between AB, bond energy between two AA atoms, bond energy between two BB atoms, Z, coordination number and Avogadro number, all are constant. So that is plugging into a sigma into XA into XP, and many times it is written sigma into 1 minus XB into XP. That is what it is, delta H mix. So you understood now how to get the delta H mix. So I am not going to do it how to get delta S mix, okay, right? We are not going to do that. That is coming from directly Boltzmann, you should do yourself. Okay, there must be some homework for you also. So what is that? Okay, what is that? Okay, let me erase it completely, leaving this part, and I will let you know. This is actually our elementary thermodynamics. I have to do it because many of you may not understand, or many of you may be finding it out of the things. So delta S mix is minus R XA ln XA XP ln XP, or minus R 1 minus XP ln 1 minus XP plus XP into ln XP. So now you know the delta G mix. Okay, I should not use mix, I should use M only because we have been using M. So delta G mix is what? Delta HM minus T delta SM. So that's becomes sigma 1 minus XB into XP plus R into T. This minus and minus sign will become plus 1 minus XA XB log of 1 minus XP plus XP ln XP. That is my delta G max, and this is quasi-chemical theory. This is something like a regular solution, okay? But there will be other models available. We are not going to do that. And what is G? G is basically G pure plus delta G mix. And what is G pure? XA, GA0. XA is the mole fraction of A. Pure A has a free energy of GA0 plus XP, GB0 plus delta GM. And this can be again written 1 minus XP, GA0 plus 1 minus XP into GB0 plus delta GM. So now if you look at carefully this equation, this is straight line, okay? That is what you see in the earlier plots, that is a straight line. This one, the first two terms. The last term shows it is a parabola. 1 minus XP 1 into XP is XP square. 1 minus XA, XP into XP square, XP minus XP square. Nonetheless, this is XP square, right? That is why you are getting a parabola. This is the reason, origin for such a kind of shapes. Correct. So now, I have spoken about 20 minutes or so. So therefore, this is something which you have been taught in thermodynamics of materials, right? So now we are going to discuss few important aspects. First, we are going to discuss about size effect on chemical compositions. That is what we need this section. What is this? Well, that is very not difficult things to understand. I have already explained you various things, so now it is easy for me to do that. It tells you that if I have a spherical particle of an alloy, this is spherical particle, okay, of radius r, of an alloy, component A and B, the composition of B or A, suppose composition B, whether it will remain same here at the surface and center, or there will be change of composition of B because of the curvature on the surface. What do you think? Obviously, it will not be same. And this will be scaling with 1 by r. So, as the particle size will decrease, this will decrease. That is the derivations we are doing it in the last lecture. Correct. And now, this is a little bit tricky. Okay. So, let us consider this as the alpha phase. Correct. So, obviously, free energy of the alpha phase can be written like this: number of moles of alpha multiplied by G of 1 mole, right. If its number of moles of alpha is n alpha and alpha per mole as free energy is G n alpha, this is the free energy of alpha. Well, here we have considered this phase to be perfectly ordered. So, entropy change is not there. You can do it, this will make things complicated only. Correct? Okay. Nonetheless, so this is basically free energy of the bulk. We have not considered sphericals, particle or not. This is free energy of the bulk, big material, alpha. So, if you want to know the total because of bulk and the surface, then you have to add gamma into surface area alpha. That is obvious, right? This is the free energy of alpha in the bulk, this is the free energy of the surface because of small size actually. This bulk means very big, there you can, surface area is very small, you can ignore that term, second term. But in a nano you cannot, you have to consider this term very seriously. Correct? Now, if you look at this construction, obviously this will consist of a lot of atoms, A and B. Okay. So, I can always write down 4 by third pi r cube is equal to, this r is the radius, so this is the volume, that is equal to number of moles of alpha into atomic volume of alpha. What is atomic volume? Volume of each atom. The volume of each atom is V atom alpha, that you multiply with number of atoms in this shell which you have done actually, that is equal to total volume, that is nothing but 4 pi r cube. So, I can write down, if I differentiate these equations with respect to n alpha, so 4 by third pi r square, and because of r cube 1 3 will come, 3 will get cancelled, dr. Okay. I think I should write this way, otherwise you will get confused, gamma and r. So, dn alpha, V atomic alpha. Why V atomic alpha will not change? Just constant number, it will not change like gamma. For a particular atomic species, the volume of the atom is fixed. So, what do you do? dr by dn alpha V atomic alpha divided by 4 pi r square. Right? This is understandable to you? It is easy. Correct? So, this is something which we will keep at the background here. Now, we will work on this equation. So, I can always do the same thing, differentiation with respect to n alpha. What does it give? This one at constant temperature, this is the chemical potential. If you look at carefully, this gives you chemical potential. G del G alpha total by dn alpha is basically chemical potential of alpha in the solution of A and B. That is nothing but Gn alpha plus gamma is always remaining constant. Gamma we should assume constant isotropic, otherwise the maths will be very messy, into d alpha by dn alpha. Obviously, it will not be d alpha by dn alpha, right? It will be it will be partial. Am I clear? Well, I can write this equation like this. Now you understand why I derive this term dr by del r by right del r by del n alpha, then n del n alpha. Okay, the second term. Why did I do? So you understand now, right? Well, what is A? What is the surface area of this particle? That is basically 4 pi r square. So what is d? This is d alpha, d del a alpha by del r. This is nothing but here di by dr. This is equal to 8 pi r. So I get this term first. I write down this term 8 pi r multiplied by p atom alpha 4 pi r by mistake so finally that's what you get. So because of small size, you get an extra term called twice gamma v atomic alpha divided by r. So you can see that the chemical potential is too much dependent on that, right? So this then further can be equated with the equations which I gave you earlier, or not this. Okay, difference of these two. Difference of these two means this term can be equated with the one which I derived in the last slide, correct? Nonetheless, we will not prolongate this mathematical derivations to make you bore too much. We come back to the actual thing, right? That can be done, anybody can do that, okay, because I have given you the equations. We can always discuss when you are having questions or so. Right. So you could nonetheless, what you can do? You can write down when you have a particle, let us not remove it, on a particle, the original problem, okay, and suppose this is the composition, equilibrium composition because of radius r, and if a bulk material very big, the composition is infinity. We can always write down twice gamma v atomic alpha by r is equal to 1 minus x b. Remember, this is r. This is an alloy of a b of alpha phase x b log of, this is nothing but what? The entropic terms, right? Okay. So 1 minus x equilibrium r 1 minus x 1 minus x equilibrium infinity plus x p log of x equilibrium r divided by x. You must be wondering how I am taking. It is as compared to bulk, right? Remember, this is total free energy, and we are subtracting total free energy minus Gn per mole actually. What is this? This differentiation is basically per mole. Okay. So, per mole basis we are doing that. Difference of total free energy minus free energy of the bulk. So, this is equal to twice gamma V atomic alpha by R. This must be equal to the entropic term. So, this is equation whatever I have written here has non-trivial solution, very difficult to solve. So, first of all, logarithmic equation, it has two unknown terms, one unknown term, although that is one unknown term, that is x equilibrium at the surface for the radius of the particle r. For the bulk it may be known for a given value of x p, but for the nano it will not be known, right. So, you need to find out that, but because the logarithmic equation you may not be able to find the solutions. So, that is why you have to make a lot of simplifications for that, and various simplifications are available, various. Okay. And if I keep on discussing, then it will take a lot of time, all the things, but I will tell you the different ways of kind of simplify these equations, correct. So, how do you simplify first? First and easiest way of simplifying this is to assume a funny assumption. What is that? Is to assume the case 1. Case 1 says that if I consider x p to be equal to 1, the moment if you consider x p to equal to 1, basically tells you it is pure B. It is not A is there at all. Mole fraction of P is 1 means mole fraction of A is 0, right. But interestingly, if you do that, then it gives you what it gives you. It gives you these things, this term goes vanish. So, I can write down twice gamma B atom alpha by R is equal to first term vanishes x p 1 log of x equilibrium R divided by log of x equilibrium infinity. So, that means x equilibrium R is equal to x equilibrium infinity exponential twice gamma P atom alpha divided by R. This is something which is widely used. Okay. But you know that the assumption involved is very peculiar, x p equal to 1. Second assumption and third assumption, which is homework for you, is that you can always assume x equilibrium R is almost equal to x equilibrium infinity. That is nothing but a bulk, right. You can try it out. It will lead to analytical solutions. Okay, and I would like to know what is analytical solutions. Please do your homework and submit. And third one is, you can always write down x equilibrium R is much less than 1 and x equilibrium infinity also much less than 1. If you do that, what does it happen? This term goes to close to 1, log 1 is 0. Then you will get the same thing. Okay? No, you will not get the same thing. What will you get? Because this is very less than 1, this is very less than 1. So, this becomes what? 1 minus this also become 1, 1 minus this also become 1, 1 by 1 is 1, log of 1 is 0, first term vanishes. So, that gives you x b what? x equilibrium r is equal to x equilibrium infinity exponential, it will be same as 2 gamma V atomic alpha r, but along with it we will have x b. This tells me when the composition of x b, equilibrium composition in bulk and this nanoparticle is very small, I mean dilute alloys. The condition 3 is for dilute alloys, very dilute alloys on the corners of the phase diagrams. That is true, correct. So, this is more logically correct. That is why this equation is much better to be adopted when you do these calculations. Okay. Now, so that is about this size and the chemical composition. So, you can see the R in nanomaterials distinctly affect the composition. So, whenever you are doing research, never accept the composition of the particle when you measure totality. You have to always measure compositions at the surface and the bulk, surface, center of the surface. Then you can consider. Center is obviously bulk because atoms are coordinated in the center of the particle. Surface atoms are not coordinated, there are a lot of dangling bonds. The compositions must be changed. And that is how you should change. This is what is the analytical formulas are talking about it. So, please remember this, and let you also do this as a home assignment. Okay, let us see how many of you do the maths properly. So, that is something which I wanted to discuss and finish up today. Okay, now I am going to discuss something new today. You know, we metallurgists and many of the ceramic engineers are interested in phase diagrams. Phase diagrams are very important, you have to understand. Okay, very, very important. Why? Because they carry information on various aspects, right? Phase stability, temperature, compositions. Okay, let us see that. Okay, so so what is the effect of size on the phase diagram? How do you deal with it? How can you deal with the effect of size on the phase diagram? Can you do it or you cannot do it? Okay. So, you can do it many ways. Normally it is done by a technique known as CALFAT. Okay. What is CALFAT? Calculation of phase diagram. Cal is for calculations, FAD phase, and D is for diagram. A very simple thing is this. CALFAT uses the concept of minimization of free energy, G, which you have used in all the calculation. That is what they do, minimize G. For a particular temperature, pressure, composition, whatever variables you have, they minimize. It is basically multivariable minimization problem mathematically. You have a pressure, constant, obviously one atmosphere in metallurgical phase diagrams, temperature is not constant, and their composition variable. So, it is a multivariable minimization of free energy is done by the CALFAT. It is a routine program which is installed in many computers. It is available in our department and many of the others also. It does it very simply. You do not need to write a code or so, but if you are interested, you can do that. What is the basic philosophy of that? So, it minimizes free energy G, right. So, as you know, G total I have already done just now. G total is G bulk plus G surface, right. G bulk is the free energy of the bulk alloys, and G surface is surface energy or excess energy which is because of the surface, right. So, as you know, I have already done G bulk is first is your for a binary alloy free energy of individual elements multiplied by the mole fractions in a binary alloy XA, XA 0, XB, XB into GB 0. What is GB 0? 0 superscript means free energy of B pure state when it is pure. Okay, because it is mole fraction of XB, that is factor has to be multiplied. Then you have an entropic term. Just now we have done that. Right. This is because of entropy change. Plus we have excess term. And what is this excess term? Excess term is nothing but, this excess term is nothing but the one I wrote, xj, xb into sigma. This derivation has been shown and done for the quasi-chemical theory, right? So that is the G bulk. Now what is G surface? G surface is, you know that, twice gamma V atomic volume divided by R. But this assumes spherical particle, right? If you want to do it for any particle, any shaped particle, you can multiply to a factor C. C is a factor which will take care of this shape change. Correct? So now you have the total free energy, G bulk, G surface, then you minimize. But when you minimize this, you also need some more information. What you need is the G V atomic volume of the alloy, that is nothing but Xa Va plus Xb Vb. Why you need that? Because you see this atomic volume, that is what is required. Okay. And what else you need? If you want, you can or may not. You can basically use this gamma, which is surface energy, also as a function of composition. There are various models available. I am not discussing about that. That will complicate the situation. Okay. So once you have all this information with you, you have free energies and the atomic volume. What do? You can simply write a code in computer, or you can basically use this online platforms available and calculate this phase diagram as a function of size. Today let us see how a few of this looks like, then we will stop. So this is the copper nickel binary phase diagram. Pure copper, pure nickel, that is the mole fraction of Ni is 1, mole fraction of C is 1. This is temperature on the y axis. Now you see the bulk phase diagram is shown by red, and for radius 5 and 10 nanometers shown, you can clearly see the phase diagram has gone down. Right, we will discuss maybe next class in detailed manner. This is for the silver copper eutectic phase diagram. You can clearly see the whole phase diagram has gone down. The bulk is shown by dotted blue, and the size aspect is shown by red and the green in solid. Indium antimony phase diagram, very funny. Okay, it shows eutectic, but no solubility on both sides. It also gets affected. We will discuss for this next class in detail about that. And also gold and platinum. So every phase diagram does get affected by the size, and this methodology I have given. Now we will discuss a bit some of these things in the next lecture to wind it up, so that phase diagram aspect is known to you. Okay, thank you.